we're going to start doing some other things with diodes. Let's set up our same circuit. As I said, let's put it in an AC waveform. Ooh, I switched out where the diode was. Shouldn't bother us too much. We have some resistor here, and we have an AC waveform. So I'm just going to call this V small s. So this is our signal. And what we want to know is we want to know this voltage of this resistor. Oops, that should be a little r. Or the voltage of this look like over time. Okay, and I'm going to do a couple things to help us understand that. The first is that basically we can kind of understand if Vs is positive, that, so here's our Vs. When Vs is positive, that diode is going to be forward biased and it'll act like a short. Okay? And so if we look at Vr of t, it should match perfectly, but then it'll be open circuited, and the reverse bias, the diode will, and it'll flatline during that period, and then it'll pop up. Okay, and it'll continue to do that. So this is Vr of t. Oops. R of t. If we look at the Vd of t, of course, it's going to look the opposite direction. It's going to be 0 voltage when the resistor is when it's forward biased. But then in a perfect world, it's going to pop up here and do this. And of course, this means that KVL still works. In other words, Vs of t is equal to Vr of t plus Vd of t. So KVL still works. Okay. Usually when we only look at the resistor, I'd call this our load resistor or something like this. But and we call this a rectifier. And in this case, you'd call it a half wave rectifier. Beauty. So, having said that, let's go do it in MATLAB. Okay, so here's MATLAB. And what I'm going to do is I'm going to make our sine wave. We're going to make an Fs, and I'm just going to make it 1,000 for this. T is equal to 0 by 1 over Fs, and then we'll do 1 second. Okay, that's probably, we'll do 1/10 of a second. Oh, we'll do 1 second, that's fine. And then we'll do our input on this. Okay, our input on this is going to be Vs, I'm just going to call it, is equal to, I'll just make a cosine wave of 2 times pi times t times, we'll do 30. That's a pretty slow rate, so we should, well, let's do 10, okay? And we plot both of those against each other, and we get a waveform. Okay. We get a waveform that looks like that, okay? And that's not very surprising that we get that on there. And yeah, I wish that I didn't have there. Okay, so we get that nice waveform there that's a cosine. And so what this is essentially doing is Vr, let's just make it equal to Vs right now. But I'm going to do find all the values less than 0. Okay, this is when we'd reverse bias it. And Vr of those values is going to equal 0. I just half-wave rectified it. We call this half-wave rectification. And then we're going to do a hold on, plot t versus Vr. I'll do it in red so it's nice and bright, and we can see that we are getting the top half of that. VD would obviously be the opposite of that. VD is going to equal VS. IDX is equal to find VD greater than 0. Oops, made a mistake. And then VD of IDX is equal to 0. Plot TVD. We'll make that one green. And you can see it's exactly what I told you. They line up on top of each other. But it's an absolute value function. Okay? So that's the basic idea of what we get out of a rectifier, at least a half-wave rectifier. Absolute value is a little bit different. So mathematically, if we were to go back to I want to do a full wave rectifier. Okay, so we just did half wave. Full wave rectifier, we have to change this just a little bit. And what we do is we say V of V, I'm just going to call it V full wave is equal to VS, okay? And then I'm going to say IDX, it's going to be the same thing. Find VFW less than 0. And we're going to say VFW of IDX is equal to VFW of IDX times -1. That should do what we call full wave rectification. I'll make this one black. And that gives us something called full wave rectification. Okay? And we'll do axis of H. Let's see what H was. Axis of 0 to 0, and I'll do the 0.21. That gives us a better idea of what we've got going on there, maybe a little bit more zoomed in version of that. And so we get a nice full wave rectifier. Can we do that with diodes? Yes, but not just with one diode. That's kind of the problem. So let's go back and look at this on the whiteboard. Okay. So we know what that half wave rectifier does, and we're happy about that. And let's just, one other thing that we can do about this is we end up, if we plot V in versus V out, and just to be clear about this, we'll call this V in. I'll put a diode like that. And this voltage here is V out. The question is, what's the relationship going to look like from V in to V out? And here the voltage is going to be 0, and they're doing a different color. And then this should be 1 to 1. In other words, at 1 volt, we should have 1 volt here. And so there's a discontinuity from V in to V out. And so this is different than, say, our voltage divider circuit. Our voltage divider circuit, V in to V out, the difference was what? It was just a straight line. Went through the origin, there were no discontinuities, and the slope indicated the scale of the voltage divider. Okay? And so I think that's what we want to look at right now for those for kind of the differences in here is we have a discontinuity. That discontinuity is going to cause problems or good things depending on how you want to look at them. Okay. Rectification, is it helpful at all? Maybe. Let's do a quick example that they have in the book. I think this one's really useful to just get an idea. We have, and they do V sub S, that's a big S. They do our 100 ohm, so they do 100 ohm okay? And this is 24 volt AC, 24 volt peak value, AC value. We have a diode here, it's an ideal diode. And then they put a DC source over here of 12 volts. And so that means that our input wave, if we're to plot it, looks like this. This is 24 volts. Okay. So they have that, and the question is, what's the voltage that we're going to get over, or what's the voltage that we get over that resistor? This is a little bit more challenging, okay? Because we have to figure out when that thing is going to be forward biased. What's the voltage there over that resistor? And as it turns out for this particular thing, we have to do just some math. And so what ends up happening is if we subtract off 12 volts, basically we get a negative bias on this, and we end up with something that looks like this. Okay, that's what the waveform is going to look like if we were to look at the waveform from here to here. Okay, and we just had a straight resistive load. We'd look and we'd see the voltage drop. It would drop us by 12 volts. Okay, you can just see this. We can flip it over here. It'd be 24 AC minus 12 volts. But the thing is that means that this diode is going to be reverse biased more often. In fact, it's going to be reverse biased except for that portion right there. And notice some things about this. Okay, first of all, we're going to erase that. Okay. This should be, it's not drawn to proportion, but that should be sitting there at 12 volts, about, okay? And we end up getting current only through that portion, okay? That's what that peak current is going to be through there. And we end up, we'd have to do some calculations to figure out how wide exactly those up times are, but it's not going to be half of the period there. It's going to be something else. And there's because we're not talking about a linear voltage going in, it's a sine wave going in. And so I don't want to go too much into this. I just want to show you that when we do weird stuff like this, we end up with we have to think about when this is being forward biased or not. One other thing, and then I think we'll break this one off. We're going to do short videos. Maybe two more. Three diodes. Time all together, put them through a resistor to ground. I'm going to call this our V out. Okay, and we're going to call this our VA, VB, and VC. Okay. And so we have a few different options for this, and what we're going to do is we're just going to put in some values for those. We'll just put ones and zeros. VB, VC, 0, 0, 0. Oh, this is looking familiar. 0, 0, 1, 0, 1, 0, 0, 1, 1. And I'm not going to go too much further than this. So if these are all low, and this is also low, 0 volts, then V out will also be low. Okay, now in this next case it's kind of interesting. VC is going to be 1, so we're going to hook this up to voltage. These guys are going to be grounded. Okay, and so that means, well, we have a low voltage here, and we have to test. There's going to be several different options for this. In fact, there are 8 different possible combinations of forward bias and reverse bias. But if we do an educated guess, we kind of guess that this is going to be forward bias, this one's going to be reverse bias, and this one's going to be reverse bias. We think so. So let's test it that way. If everything works out well, we'll do this. And we'll just do a 1 ohm resistor right here. And what we'll do is, that means, so if this is true, forward bias, let's replace all these with how we think it's going to shake out. Okay, just like that. And we come through and we would get a positive current that goes through there. So yes, that one would be forward biased, at least so far. And then these guys would have 1 volt, here, and 0 volts on the other side, which means they're reverse biased. That's great. But what's the output going to be? 1 volt. And if we do this again and again, so what do we get with this? This is an OR gate. Okay, so that's a digital logic OR gate. Well, if there's an OR, there's an AND. Okay, AND. They take this up to 5 volts, that's fine. It's slightly different than the 1 volt I had, and then we have VA, VB, and VC. This is our Vout. And we're going to do the same thing. 0, 0, 0, 0, 0, 1, 0, 1, 0. You would know that when I say 1, I mean 5 volts. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. For A, B, and C. If all of these are grounded, Vout is going to be 0. Okay, now I'm going to have this guy hold high and these two guys grounded. And so what we would expect for that, we might expect this one would be reverse biased. And so we'll open that one up. These two guys will be shorted. And I think that that's all going to be true. So what's Vout going to be? Well, because current is flowing these guys this way through these, we end up with a 0. And it turns out if any single one of them is grounded, that they'll produce a 0. But not if all three. If all three are high, that's going to put it, I'm going to say marginally biased, because these guys are going to be 5 volts. That's kind of weird. So let's put 5 volts at each one of those. And so if there's a question, if current is flowing, we're going to say no, there's no current flowing. So that's going to be on the edge or reverse bias. It's not really reverse bias, it's just kind of on the edge. But we can see that Vout in this particular case is going to be 5 volts. And if there's no current flow, so 0 current flow, it's kind of reverse bias. It's right on the edge. So those are the examples I want to show you. There's one more that we can get to. Before we stop. And this once again requires multiple diodes. So that's a ground, not a diode. This is D1. There's another diode here, D2. This goes up to 10 volts. We'll put a 10 kilo ohm resistor here, and we'll put a 5 kilo ohm resistor off of these guys down to negative 10 volts. And our question is, the question we have, we want to find out what the voltage is here. What the node voltage is. We're going to call this Vout with respect to ground, negative 10 volts, 10 volts. And so we have one of 4 possibilities, D1, D2. And I'm just going to denote 1s and 0s as forward biased and reverse biased. And what we're going to do is we're going to look at these as, we have to, I don't know how they're going to be forward biases a 1 and reverse biases a 0. I think we can go ahead and say this one is probably not true. I think that D2 is always going to be forward biased, and so I also, oops, not that one. And so I'm going to eliminate that one as well. I have a hard time believing D1. So let's just try those two. If not, this is the most likely case. And so we're just going to pick one, and I don't care which one. We can do a 50-50 split. We'll do one another way here in just a second. But as we look at this, we'll do it this way. And what that does, I'm just going to put a short here, and open here, and we have to test. Okay, so what's Vout going to be if that's the case? Ooh, this is a fun problem. This turns out to be okay, negative 10, positive 10, 10K, 5K. What's our voltage here? And so this ends up being 20 volts times 5 divided by 15, and then we have to subtract 10 volts. We can go through that in more detail, but that's back to circuits 1 type problem. Or you can do superposition. There's all sorts of different things we can do. So what's 20 times 5 divided by 15? 20 times 5 divided by 15 is going to be, let me see, 6 point. I gotta get MATLAB going, man. Okay, so 20 divided by 5. Can almost see MATLAB. 20 times 5 divided by 15 is 6.66 volts. Minus 10 is going to give us negative 16.66 volts. Okay? And then we go through and we say, is this true? Because we're testing this case right here. We're going to, so negative 16.66 volts, that means here is also negative 16.66 volts. That would indeed have current flowing that direction. I like that. Now, this was our anode and our cathode. Is the voltage here greater than the voltage here? And the answer is no. It's not true. Okay, let's start over. So we're going to test this one next. That's where these are both shorted. Okay, this is still negative 10 volts. Okay, and now we end up with a weird thing. So that means this voltage here is going to be 0. V out would be 0 volts. It makes the math on this obviously a lot easier. But let's see, 0 volts here. Okay, that means this is going to be tied this way. The question is, do we have positive current flowing this way? Okay, and the only way that we're going to know is I'm just going to call them I1, I2, and I3. We have to figure out if I3 is positive. So I1 would be 10 volts over 10K. I like that. That's 1 milliamp. I2 would be 10 volts over 5K. That's going to be 2 milliamps. And by KCL, I3 would have to be, let me see, it would have to be I3 plus I1 minus I2 has to equal 0. Can we see that? Yep. And just solving that over here, we come up with I3 is equal to I2 minus I1. This would give us 1 milliamp. That is true. This is the case. It's both forward bias. So this gives you an idea of when it's more complicated. Now, when it's more complicated, 2 diodes, it wasn't obvious to us which ones were going to be forward and reverse biased. We had to test. Let's do one more thing. Exact same circuit. Almost. This is D1 again. This is D2. This is 10 volts. But this is now 5K. And this is now 10K. And so the question is, which one is it going to be? Well, fool me once, right? So we're going to come back here and we're going to say it looks awfully a lot the same. Let's shorten both of these D1 and D2. And let's find out that current. So we come through and I call this one I1. We call this one I2. Call this one I3. I1 in this case is 2 milliamps. I2 is going to equal 1 milliamp. Why? Because 10 volts, 10K. Okay. Because this would be 0 volts because that's a shorted diode. And then, milliamp. And that means I3, same math, is equal to I2 minus I1 is equal to minus 1 milliamp. And you say, uh-oh, that means that we are in trouble. That's not necessarily the case because that would reverse bias this diode. Okay, we made an assumption from before. So what we're going to do is we're going to go back to everything that we did, and we got to go. All right. Well, shoot. Now we have to treat it like the circuit that's no longer 0 because that diode is a forward bias. And we have to come through here, and we end up with the same voltage divider that we had before. Okay? And so we end up with just these 4 elements: voltage, 5K, 10K, negative 10. Let's go through this. I went through it quickly before. Let's do it slower now. Okay, this is negative 10. This is positive 10, 5K, 10K. Okay, and I'm going to do something that's sneaky, but since we're looking at the reference voltage, we have to undo it. But this, we're going to swap over. We have 10 and negative 10, but they're opposite. So that's going to give us 20 volts and a voltage divider, 5K, 10K. That's what I did before. I went really quickly before. But what that's going to give us for a voltage here between these guys is something that's going to be like 13.33 volts. But this before was referenced to ground. Okay? That's in between here, and so in order to get there, I actually have to subtract off 10 volts from both sides. In other words, I added 10 volts to everything, and now that I have my solution, my 13.33 volts, so the voltage divider I have to subtract off, and this voltage here ends up being 3.33 volts. If you don't believe me, do it multi-sim and see how it comes out. And now we ask the questions, does this make sense? We will have a positive current here because we have a higher voltage, lower voltage, and a resistor. That one looks good. This voltage is higher than ground, and so this is reverse bias, and I'm happy with all of this. The only other thing that we'd have to do is figure out currents through all of these. That's not hard. 13.33 volts divided by 10K, so that's going to give us 1.33 milliamps going here, and it's going to be the same here. 1.33 milliamps is going to be going through that one. So there's our whole mathematical camboozle for this first problem, and the second lecture of this is done.